Welcome to the mid-morning parallel session. This session is Modern NFL Analytics, Defense, Movement, and Strategy. Our first speaker is Ben Jenkins. Ben Jenkins works as a data scientist for Apple and is a PhD student at Florida Atlantic University. He's particularly interested in the intersection of statistics and sports and how we can use statistical techniques to generate insights from player tracking data. Let's welcome Ben Jenkins.
Appreciate it. Thank you. Yeah, of course. Hi, Kip. Can everybody hear me? Yeah, we're good? All right. It fell. 1 second. Sweet. So I'm going to discuss about how we can apply causal inference techniques and causal modeling techniques to estimate the impact of defenders with using multi-agent transformers. A lot of jargon, but I'm going to go into that. Okay. So here we have a example play, where we have the offense in blue, defense in red, and we have ball carrier who is Saquon Barkley, and this is a running play. And so right here, Saquon Barkley gets tackled for a 6-yard loss by Jeffrey Simmons. And so the question is, who gets credit for this tackle? So who's responsible for the outcome of this play? Traditional metrics such as would only provide the tackler with credit on this play. The reality is multiple defenders contributed causally to this outcome. And the question we want to say is, how do we measure what doesn't show up in the box score? The goal here is to use tracking data to answer counterfactual or what-if questions that help us better identify the contributions of each player on a play. So this is using NFL player tracking data. For those of you who don't know, the NFL has RFID chips on the shoulder pad of each athlete, which get the XY coordinates, so their location, their acceleration, their direction and orientation every 1/10 of a second for all 22 players. And so this is from the 2024 NFL Big Data Bowl, focused on measuring tackling performance, specifically the first 9 weeks of the 2022 season. Now I'm going to briefly talk about the difference between supervised learning versus causal inference. So supervised learning is going to ask what will happen or what's likely to happen given the historical data. It's mainly prediction-based, so you can, given player positions and information, we can predict EPA outcome or some outcome of interest. It's correlation-based, so the goal is to find historical patterns in the data, and some goal is to minimize some prediction error and have the highest accuracy and performance. Some problems with supervised learning is there's often some confusion between correlation and causation. I show how they're biased towards high-volume tacklers, and also it's hard to disentangle skill with opportunity. Causal inference, on the other hand, asks what would happen if something else happened, right? And so it's counterfactual based. So we want to say, what if this defender didn't make this tackle on the play? What could have been the outcome? And then we can actually measure what is an individual's contribution. It's causation based, so we want to try to isolate the cause and effect or understand the underlying data generating process. The goal is to estimate individual treatment effects, or the conditional average treatment effect, which is the difference in the outcome of a play if a player tackled versus didn't tackle on the play. Some key advantages are it isolates individual contributions, it accounts for situational context, as well as helps to separate player effects from team effects. And so the bottom line here is that prediction is not the same thing as attribution. For estimating player contributions, we need to understand the causal understanding, not just predictive accuracy. So we have a defensive attribution problem in football. What I mean by that is you may have two players, let's say player A and player B. Player A has 8 tackles, player B has 2 tackles, and so which one is better? And so the challenge here is that defensive value is largely invisible in traditional metrics. So coordination and positioning matter a lot more than just the final contact. And there's also a counterfactual question that needs to be answered, which is, what would happen without this defender or without his intervention? So one common approach that I think was discussed this morning is a residual-based approach for player attribution. So the common approach is, let's train some machine learning model, can be anything from a linear model to a tree-based model neural network, and let's predict some outcome of interest given a subset of features. And so we're going to create some expected value, which is the conditional mean given a set of features, and we're going to use the residual, which is the difference between the actual value and the predicted value, and we're going to use that as the unexplained performance of a player. And so let's attribute residuals to individual players. The problem of this is that residuals capture unexplained variance, not causal effects. And so there's many reasons why you have a residual value. That residual value is what the model is unable to predict, and it makes a strong assumption to assume that the residual is fully explainable to that player's ability. Also, there's no counterfactual framework with residuals. They only ask, what did we fail to predict? They don't ask what would have happened if without this player, without this player's actions. And so these are asking fundamentally different questions. Lastly, machine learning residuals can conflate a mixed individual skill with teammate effects, right? So it's hard to say, is player A good, or did player A benefit from player B? There's also coordination effects, which can be misattributed to individual players. There's also selection bias, so players in different situations generate different residual patterns. There's no mechanisms to ensure fair comparisons, and it sort of creates an apples to orange comparisons. So an example of this could be Aaron Donald gets 0.3 EPA residual, and the question is this because he's an elite player, or was the offense already disrupted by his teammates, right? And so residuals have a hard time distinguishing between these two things. And so residuals measure predicted error, not necessarily causal contributions, and player attribution requires explicit counterfactual modeling. So why current defensive metrics fail is tackle counts, miss anticipatory positioning, correlation-based models struggle and cannot answer what-if questions. And so we need causal inference. Okay, so here's an example of a play here. And so one of the assumptions we make in causal inference is the stable unit treatment value assumption, or SUTVA. And this assumes that units don't interfere with each other. And this is violated in football because defenders coordinate extensively, and so they work together. So we can see here in blue, the blue players are the defenders, red is offense, the running back has the ball. And throughout the play, the defenders have to work together, right? And we also have dynamic confounding, so teammates are going to confound, and as well as we have temporal inference here. And so we want to look at how it changes over time. And so if we just look at maybe 1 second into the play, what happened previously in the play can affect what happens next on the play. And so the goal is to create a multi-agent system. And so what is a multi-agent system? The traditional approach could be to analyze each player independently, but we want to model all 22 players simultaneously as interacting agents, where each agent is a player, and they're influencing and responding to each other in real time. And so football requires this because defenders don't act in isolation, they work together, right? One defender's movement can affect the optimal actions for teammates, and traditional methods assume independence, which is violated. We specifically want to model 3 types of agent interactions. These are coordination, interference, and substitution. So coordination is how defenders work together, such as like coverage schemes or gap assignments. And we also want to measure interference, which is how one defender's actions affects other teammates' effectiveness. Lastly, we want to measure substitution, which is how defenders compensate when teammates are out of position. And so technically, we implement this using transformer models. And the attention mechanism allows us to learn which players influence each other, spatial relationships captured throughout the play and show the learned attention weights. And we also have temporal dynamics, so we can model how interactions evolve during the play. And so the key insight here is that football is a very complex sport and a system where individual value emerges from collective behavior. So an example of this is if you're interested in, for example, modeling a flock of birds, you can't just model the individual flight patterns because they depend on the entire group, not just those individuals. So our causal framework is we set the treatment as a binary indicator, so whether defender I made a tackle on the given play. The outcome is expected points added, so how much the offense benefit. EPA is a widely adopted metric that measures the efficiency of an offense, and the goal is to estimate the expected value of EPA, right? Given the defender didn't make the tackle, minus expected EPA if the defender did make the tackle on the play. And this creates expected points saved, which tells us how much benefit did an individual have in terms of his tackling ability. And so the key innovation here is we use multi-agent modeling. So we have a transformer architecture, which processes all 22 players simultaneously. We have attention mechanisms to capture defender coordination, and we want to explicitly model those 3 interference effects we talked about before. So coordination, substitution, and those competition effects. So we can see on the right, which is the DAG, which the green are the confounding variables that we're accounting for. So we have the player features. This includes the X, Y coordinates, their speed, orientation, direction. We have information of the ball carrier, so the tracking data for the ball carrier. We have relational features, so how each defender relates to the ball carrier. We also have teammate features, right? So each defender has as 10 teammates. We also have the opponent features, and then we have game context, so like what down is it, yards and distance, and we're trying to estimate what is the effective tackling on expected points added. And so we have a selection bias when dealing with this data because the problem is defenders don't tackle randomly. The data is not random. There's a reason why somebody made a tackle on a play. And to address this, we use a variety of techniques. So one is MMD balancing, which helps to match distribution across treatment groups. We use adversarial training, and so where a domain classifier can't distinguish between between the treatment and control groups. We have also representation equilibrium, so we want to have similar covariates, which leads to similar representation. We use doubly robust estimation, which combines propensity scores and outcome modeling, and only requires one of the two models to be correctly specified to be able to identify the causal effect. And this helps provide consistent estimates even if only one is wrong. And this helps to create a more apples-to-apples comparison for valid causal inference. And so we can go back to that first play that I showed in the beginning, and we can see actually the EPS for each defender on this play. And we can see here that traditionally, only Jeffrey Simmons, the tackler, would get credit. We can see there's about four players that are contributing positively to this play. And so we can see that our model identified that Jeffrey Simmons is the best performer in this play. There's also players such as Tartan Weaver who have consistently high performance. And so these interior defenders help to limit running lanes, which help get the opportunity for Jeffrey Simmons to make this tackle. And so our framework can capture coordinated defensive effort, not just the final tackler on a play. And so this identifies setup players who are typically invisible to these kind of metrics. Next, we look at missed tackles. This is a play of Russell Wilson passes to Javonte Williams, and he breaks two tackles, right? And so what happens here is the model can identify the failed tackles as well as damage control. And so there's some players who were actually performing decently well because they're actually showing a strong pursuit angle. And we can also show what are the cascading effects. And so from Woolen and Coleman. So the insight here is we can capture both failure costs and recovery value in real time. And so validating causal models is quite a bit different than traditional ML because the fundamental challenge of causal inference is we only get one outcome for each individual, and we don't know both potential outcomes. And so how do we know that our causal estimates are valid or are correct, right? And so with traditional machine learning, you may just do some cross-validation techniques to be able to measure how well your model generalized to unseen data. This can tell us about predictive accuracy, but doesn't tell us about the underlying causal mechanisms. And so with causal inference, we need the certain things we can do is we can create synthetic data where there's ground truth, so we know the underlying data generating process, and we can measure how well a model is able to identify the causal effect. There's also aggregation tests we can do, and most importantly, there's sensitivity analyses. So we can run a variety of analyses to measure how sensitive is your causal estimate to your assumptions that you made in the process. Lastly, you can look at counterfactual coherence, looking at how well the distributions line up. So the key insight here is causal validity requires fundamentally different validations than traditional predictive accuracy. Now we can look at individual case studies. So let's look at the data set. We can look at Aaron Donald, who's known as one of the best defensive players, recently retired. And we can, in the top figure, we can compare his two distributions. So the EPA when he doesn't tackle and the EPA when he tackles. So the EPA when he doesn't tackle is blue, and you can see it's much farther to the right versus his distribution when he does tackle, right? And so we can look at the difference between this, and this is the expected points saved metric. We can see Donald's expected points saved is 0.268, and that means that each Donald tackle prevents around 0.27 points. Expected points. And we can see here there's a clear separation between treatment and control, which helps to validate the causal identification for its individual player. And then we can also create confidence intervals to measure uncertainty regarding the small sample size. Now that we've done that, we can then aggregate to the season level or the 9 weeks of data. And we can show the top 10 players in each position. So we can show the top 10 defensive ends, top 10 inside linebackers. On the top right is the top defensive tackles, and these are inside linebackers. Important to note that 16 of these 40 players were identified as all pros in that year, so widely regarded as one of the best players in the league. It's same with Pro Bowl. We have 18 players as Pro Bowl. So this shows that the causal model is able to identify the best players. Next thing you can look at is, now that we know that it shows some beneficial in the individual effects, we can look at the team effects. And we can see that on the x-axis is the mean expected points saved, so our metric, and on the y-axis is the mean expected points added during tackle plays. And we can see there's a strong negative correlation here, which is what we want, meaning that teams with better tacklers tend to have better outcomes. And this explains about 41% of variance in tackle play outcomes. And so it's important here to note that the individual causal estimates can capture genuine defensive value, not just statistical artifacts. And so this framework can help teams distinguish the best defensive teams as well as players. One of the key insights we found in this modeling is that specifically by modeling these interference effects, we found that 68% of plays in the data set show significant interference effects. And if you do not specifically model this in the data process, you're going to lead to biased results. On the top left, we have a figure here that shows the interference correlation versus distance, and we see here that the amount of correlation drops from 0.52 within 5 yards to below 0.11, which makes intuitive sense. If we look at the right figure, we can see the black dot represents a reference defender, and they show the coordination zones. And so we can see here, the farther away a defender is from that other defender, the coordination drops. Next, we can look at positional heterogeneity and tackling expected points saved. So this just shows the distribution of expected points saved by position. We can see here, notably, we can see center backs, free safeties, and strong safeties. They tend to have distributions that are below zero with wide spreads. And this is a result of context. So tackles occur typically after the offensive gain advantage for these players. And so there's three scenarios. So one is that they successfully offensive execution, as well as competitive coverage breakdowns and pursuit to situations. We see the front seven, which are these green. We see here they have much higher, much more positive. And so the key information here is that defensive backs, most value comes from before they tackle. So it comes from coverage as well as preventing the gain on the play. Next, we can look at our validation. So one of the validations we used GANs to create synthetic data, and so we're able to actually know what the underlying causal effect is, and we find that our framework has a much stronger ranking correlation in terms of understanding the causal effect compared to some traditional ML like XGBoost or other neural networks. And so the key insight here is that if you just maximize for prediction accuracy, right, you're not necessarily going to get causal recovery. We also showed some baseline models, and so we compared XGBoost as well as some other linear models and nonlinear models, and we found that XGBoost has strong predictive accuracy, right, which is expected, about the same comparatively to our causal model, but XGBoost causal correlation was only 0.34 compared to our 0.81, right? And so, and we also found that traditional ML was biased towards high volume tacklers, so the players who had a lot of tackles. Next, in terms of validation, we can look at propensity scores. And so propensity scores are important because they're estimating the probability of treatment. In this case, is making a tackle. And we want to balance accuracy versus overlap. And so what I want you to focus on is the discrimination is 0.83 on training and 0.82 on validation. And we see that the AUC drops during post-balancing in the orange, which is what we want. So we ideally want a similar to a randomized controlled experiment where there's no difference between the treatment and control group. So we say it's able to decrease it, but however not to 0.5. And so this just shows that we're able to maintain discrimination while achieving balance. Next thing we want to look at is calibration analysis, so how well calibrated our model is. And so this just shows for the training set as well as the test set, and this just shows how well our observed probabilities align with our predicted probabilities, and this, we see reasonable estimates here. Lastly, we ran sensitivity analysis. So you can think about this is if you were to, one example is a placebo test. And so what we did here is we changed the treatment with actually a placebo, and we found that our results went to 0, which is as expected. We also ran Rosenbaum bounds and found that we have moderate sensitivity to unobserved confounding, which is to be understood and kind of makes sense given the data. And so in conclusion, this is the first multi-agent causal inference framework designed to measure individual defensive effects or evaluation in football. We have explicit modeling of these interference effects that capture 68% of plays with significant effects. We use multi-agent transformers to handle the complex 22-player interactions. We use doubly robust estimation to help protect against model misspecification. And our key findings are that traditional metrics systematically undervalue coordinated defenders. We find a significant bias reduction compared to independence assumptions. Through synthetic data validation, we found that our method has a much higher correlation with the actual underlying causal effects than traditional supervised learning. And we also found that our team level, our individual estimates aggregate meaningfully to team-level validation. So we can not only estimate who's good at defense, which individual players, but we can also scale that up to the team level. So wait 1 second. Okay, so some broader impact is, so why is this important beyond football? So this demonstrates how we can apply causal inference in complex multi-agent settings. This addresses interference effects that's common in team sports. This is a strong template for attribution problems in other domains, and helps in terms of practically we can help evaluate players in terms of contract decisions as well as defensive scheme optimization. So there's some clear limitations. It's only nine weeks of data for the 2022 season, so it limits generalizability, so how generalize all these findings to other seasons. We found moderate sensitivity to unmeasured confounding, which is to be expected given this data set and complexity. The binary treatment definition can kind of simplify the continuous defensive involvement in plays. And for future directions, I'd like to run out more seasons, integrate offensive player modeling, and extend other team sports. Yeah, thank you for your time. Any questions?
We have time for questions if anyone wants to ask a question.
Hey, thanks, Ben. It's a really nice talk. Have you thought about, as a form of either validation or probably even more an extension of what you're doing, consider tacklers' performance over consecutive seasons, particularly seeing whether tacklers who perform well one season maintain their strength?
Yes, it's a great point. So we only had 9 weeks of data, but I didn't show it here. But I did find that if we compare just like the performance of the first 4 weeks compared to the last 5 weeks, we actually see some stability over there. And so we'd expect to see some stability. If I had more data, I would like to see that. How well does it correlate over time? And you should, if you're understanding the underlying causal effect in the data, it should show stability. Yeah. Throw it. Touchdown.
Great talk. I'm curious about, how do you think about the uncertainty in the attention of the transformer and how that could propagate into these estimates?
Yeah, so that's a good point. Yeah, so one way I wanted to explicitly model uncertainty is using variational inference. And so I actually kind of created Bayesian networks to be able to quantify their uncertainty, but that is something I could look into more. Yeah.
This is a lot of work, Mark.
So were there any players that were seen as weak by your model that you thought are strong? And maybe like why, if that's the case?
Yeah, I think for this problem, in causal inference, we have to think of a treatment. So the treatment in this case is tackling. And I'm only measuring like what's the effect of a player's tackling ability. And so there's a lot of other things in a football play other than tackling. And so there's some players that may show up good in tackling or actually bad in tackling, but there's other metrics. So like if I go back to, for example, sorry, 1 second. If I go back to like defensive backs, like cornerbacks, right? It doesn't mean that these players are bad, right? It just means that the context in which it occurs, typically the offense already gained an advantage. And so if I try to create some modeling to measure defensive backs, I wouldn't focus on tackling, I'd focus on how well they're able to cover it as well. Yeah.
Thanks for the talk. I'm curious a little bit about the sort of dynamic nature of the propensities in this context, and in particular as like tracking data, as your frames get kind of closer together, some of these propensities can get very like close to 1. And I'm curious how you think about that, especially kind of extrapolating to other contexts. Yeah, I'm thinking about some of the contexts in hockey, for example, that propensities close in time would end up being very close to 1. And yeah, how do you think about that?
Yeah, that's a good question. Yeah, so you will see like, yeah, because it's frame based as over time, as you said. And you can see that some of the propensity scores can be close to 1. One thing you want to make sure that there's overlap, right? And so sometimes they have clipping in causal inference. So you want to clip kind of the estimates that are close to 1, right? Or closer to 0, but yeah.
If you could go back to the slide with the different positions.
Yes. Sorry, 1 second. Yeah.
Like in theory, if a cornerback or a safety is making a tackle, the other team has probably already got past the line of scrimmage. So like, how do you think about that in like this EPS context?
Yes. So the EPS context is saying so for these values for the quarterbacks, free safeties, and strong safeties, it's saying that what's the difference in the outcome of the play if If they didn't tackle versus they tackled, and the negative values exist exactly as you said, because when they tackle, the offense already gained an advantage. So if they actually do tackle on this play, it's going to be bad for the defense, hence why it's negative here. If that makes sense. Yeah.
Very interesting talk. I'm just, this is more of a comment, but I like your perspective in terms of context matters and the ability to look at context. I wonder if you could apply this type of analysis to, let's say in football, to a special teams punt return touchdown. Because typically in the box score, the punt returner will get the glory, will get sort of the accolades of having scored the touchdown, but you could be able to use perhaps this methodology to identify a key block, a key missed tackle, but maybe a key block that allowed the opportunity for the returner to make the big play.
Yeah, no, great point. Yeah. I agree.
Serious?
Chuck it. Aaron Rodgers, hair Melly, do it. Yeah, I know, right?
Hi, great talk. I like it. I have a question also about this plot and sort of what it's saying. Correct if this is wrong. I think you're saying that essentially cornerbacks are making tackles where the team has already lost an advantage, right? Or that the ball's already 20 yards downfield. There's been a positive play for the offense. This is a plot, though, of expected points saved, right? So this is this like the difference between whether they made a tackle and didn't? Or is this something else? Because I feel like if it's the difference between them making a tackle and when they didn't, not making a tackle is almost always worse than making a tackle. So I'm curious about how you're getting negative values in the expected points saved statistic.
Yeah, great point. So this is using from the whole entire play, right? So you are right. If I were to subset it on just when the tackle occurred, right, just when the frame in which the tackle occurred, we wouldn't see these negative values for defensive backs. We only see it because, for example, if we start the play and then before the 20-yard gain, it's saying if this defender made the tackle, if that makes sense. And so what we're seeing is that these negative values exist because early in the play, it's bad if these defenders made the tackle. But actually, if we were to subset it only on the frames in which the tackle occurred, we would not see those negative values because actually it's a good thing if the defender made the tackle on that point. Because if he didn't, then it'd probably be a touchdown or additional gain. Yeah, so that's a good point.
All right, let's thank our speaker.
Thank you.